All right, we have come down to the very last section of our Calculus 2 course. In this video, we will be going over section 6.5. This section is about differential equations. Okay, we are going to talk about various types of differential equations and some techniques to solve certain differential equations. All right, first, I want to define what we mean by a differential equation. Okay, before a differential equation, what do you mean by an equation? Okay, remember, equation is two mathematical expressions connected by an equal sign. For example, this is an equation: 2x plus 1 is equal to 5x plus 3. As you can see, two mathematical expressions are connected by an equal sign. Okay, this kind of a statement is called an equation. Okay, then what do you mean by a differential equation? Differential equation is an equation involving derivatives. If an equation has derivatives, we say that it's a differential equation. For example, this is a differential equation: dy over dx plus 3x is equal to 0. As you can see, this is clearly an equation because we have the equal sign and you have the derivative involved in that equation. Then we say that it's a differential equation. Okay, then we can categorize differential equations further as first order differential equation, second order, third order, so on and so forth. Okay, what do you mean by a first order differential equation? We say that a differential equation is first order, only the first derivative is involved. For example, this is a first order differential equation because only the first derivative is involved there. Then you should be able to tell me what we mean by a second order differential equation. Second order differential equation means second derivative should be involved. Plus 3x is equal to 9x squared. Okay, so as you can see, this is a second order differential equation because the second derivative is involved there. Okay, so on and so forth. You can define the order of other orders of differential equation accordingly. Okay, all right, next thing I want to talk about is what do you mean by a solution to a differential equation? When do we say that a certain function is a solution to a given differential equation? Well, let's take an example. Let's look at this particular example. Clearly, this is a differential equation because you have the equal sign. Two mathematical expressions are connected by an equal sign, and also the first derivative is involved. So clearly, it's a differential equation. Okay. Now the question is, what do you mean by solving this differential equation? Or what is the solution to this differential equation? Okay. Remember, solution to this differential equation is any function y that satisfies this differential equation. Okay, to find a solution to this differential equation, you need to find this function y. You need to find y as a function of x that satisfies this differential equation. Okay, can you find such a y? For example, would this be a solution? Y is equal to x to the power 3. Would this be a solution? If it is a solution, when you plug in your y here, it should give you x cubed, right? So what happens if you plug in x cubed here for y? That is dx cubed over dx, that is 3x squared, right? The derivative of x cubed is 3x squared, which is not your right hand side, which is not x cubed. So that means this is not a solution. This cannot be a solution to the given differential equation. What about this one? Would this be a solution? C is any constant, okay? C is any constant. Would this be a solution to this differential equation? Well, let's go ahead and plug in the value of y. Y is x to the power 4 over 4 plus c. If you plug in that here, you get the derivative of this one. The derivative of this one is exactly x to the power 3, right? As you can see, dy over dx is exactly x to the power 3, which is your right hand side of the differential equation. So that means this particular y satisfies this differential equation. If you plug in y here, it gives you x cubed. Okay, so this y satisfies the differential equation. We say that this is a solution of our differential equation. As you can see, it is not a one solution. You have a family of solutions. This c can be any constant. Okay, so in that case, we get a family of solutions to this given differential equation. All right, that's what we mean by solving a differential equation. Find y satisfying differential equation. All right, let's move on. Okay, next, I want to go over this theorem 6.16, differential equations whose solutions are antiderivatives. Okay, the solution of a differential equation of the form dy over dx is equal to g of x is the family y of x is equal to g of x plus c of antiderivatives of g of x. Okay, what this theorem simply tells you is that to solve this differential equation, all what you need to do is find an antiderivative of this one. Find the family of antiderivatives of g of x. If you can find the family of antiderivatives of g of x, that family is going to be the solution to this differential equation. That can be written this way. Y of x is equal to the uppercase g of x plus c. C is a constant. Okay, because of this constant, we get a family of antiderivatives, right? This uppercase g of x is, of course, a particular antiderivative of g of x. Okay, this gives you a way to solve this differential equation. Okay, so let's look at an example. Actually, I want to go to the same example that I took earlier. Let's take this example. And actually, before I go to that example, I want to define what we mean by an initial value problem. Okay, under this remark, I define what we mean by an initial value problem. A differential equation of the form dy over dt is equal to g t comma y with initial condition y of t of 0 is equal to y of 0 is called an initial value problem. Basically, if you are given the initial value, okay, when t is equal to a t naught, the y value is y naught. Okay, this kind of a condition is called an initial condition. If you are given an initial condition alone with your differential equation, that problem is called an initial value problem. Okay, all right. Now let's go and let's go to an example. I want to look at this example and try to see if I can apply this theorem, theorem 6.16 to solve this problem. Okay, so this is clearly a differential equation of this form, right? The only difference is that instead of the variable x, I'm using the variable t. That's okay. See, in the right hand side, you have a function of t. Here you have a function of x. That's okay. It's just a difference in a variable. That doesn't cause any problem. Okay. All right. So how do you solve this differential equation according to this theorem? To solve this differential equation, all what we need to do is you need to find an antiderivative of this function. That means you need to find an antiderivative of this function. We all know how to find an antiderivative of this function. An antiderivative would be t to the power 4 divided by 4, right? To get a family of antiderivatives, you add c to that. So this is the solution. Y is equal to t to the power 4 plus c is the solution to this differential equation. Okay. All right. Let's move on. Actually, one more remark. If you are given an initial condition with this differential equation, in fact, you can find this constant c. Okay, you can find the numerical value of this constant c if you are given an initial condition, but in this case, we are not given an initial condition. All right, let's move on. Okay, the next thing I want to talk about is a technique that we can use to solve differential equation, which is called separation of variable. Okay. For that, we have this definition. Let's go over definition first. We say that a differential equation dy over dx is equal to gx comma y is separable if we can write it in the form dy over dx is equal to px times qy for some functions p of x and q of y. What does that tell you? Suppose you have been given a differential equation of this form, x squared plus xy. Okay, would this be separable? This is your gxy. Notice that if you compare this differential equation against this one, this is your gxy. right? That is your gxy. If you can write this gxy as a product of two functions, px times qy, a function of x times a function of y, then it is separable. Let's see if we can write this as a product of two functions, one of which is a function of x, the other one is a function of y. As you can see, if you factorize this, you will see that actually, let me make a small change here. I'll take x here instead of x squared. Okay. If I pull out x, you get 1 plus y. Now, as you can see, you have two functions. This is your p of x. This is purely a function of x, and this is purely a function of y. So this can be viewed as your p of x. This is purely a function of y, that is q of y. So that means this differential equation is a separable differential equation. Okay, definition is very simple. If you can write your right-hand side as a product of two functions, one of which is a function of x, the other one is a function of y. Okay. All right. Now I want to go over a theorem which explains the importance of having this having a separable differential equation. Okay, separable. If you have a separable differential equation, we can actually solve that differential equation using certain techniques. Okay, that's what I'm going to talk about next. Here is the theorem I want to go over now. Solving a differential equation by separation of variables. If you have a separable differential equation, you can use this technique to solve that. That technique is called separation of variable. Here is the statement. Given a separable differential equation, dy over dx is equal to p of x times q of y, it follows that integration 1 over qy dy is equal to integration px dx. All what you do is you rearrange this one. You bring this qy term to the left-hand side as 1 over qy, and then you multiply this dx to the right-hand side. That's when you get this one, right? Actually, it's just for you to understand. I just explained that way, but you can, of course, prove this one. Okay. All right. Let's. Oh, by the way, we have a small remark here. That is solving both of these integrals and then solving for y of x, if possible, yields a solution of the differential equation. Or in other words, to find the solution of differential equation, what you need to do is you need to find this integral, you need to calculate this integral, and then from the resulting equation, you can isolate your y or solve for y. Okay, that will give you the solution if possible. If you cannot solve that equation for y, your solution is given implicitly in that equation. All right, let's move on. All right, next I want to go over an example. Solve each of the following initial value problems. As I said, along with the differential equation, if an initial condition is given, we say that it's an initial value problem. Okay, this is an initial value problem because an initial condition is given. You can view this initial condition as the value of the variable y when time is equal to 0. That's why it's called initial value problem. Okay, initial means time is equal to 0, but that doesn't work in every context, but just to get an intuitive idea about an initial value problem. All right, let's say we want to solve this differential equation, this initial value problem. How do you approach this? Part A. We can use the separation of variable. Okay, to apply the separation of variable, as you can see, you don't see any function of y here, right? For the purpose of separation of variable, if there is no function of y, if it is only a function of x, you can view your function of y as 1. Okay, for the purpose of separation of variable. So what I'm going to do is I'm going to rewrite this differential equation this way. dy is equal to sine x dx. All I did was I brought this 1 as 1 over 1 to the left-hand side. It becomes just dy. And then I send this dy to the other side using the previous theorem. If I have a differential equation of this form, I can bring this qy to the left-hand side as 1 over qy dy. It becomes an integration, of course. And then in the right-hand side, you have integration of px. That's what exactly I did here. I need to put the integration sign. Okay, so now I need to solve this integrals in both sides. How do you solve this one? This is just y, right? This is equal to, you might be wondering why I didn't put a constant when I integrate my left-hand side. I will put a constant when I integrate my right-hand side, okay? Because you don't have to put two constant in either side. You can, of course, move those two constant to one side and take a one constant, right? So I'm going to put a constant only in the right-hand side. What is the integration of sine x? Which is minus cosine x plus c. Now I put the integration constant. Okay. Now remember, this is an initial value problem. Initial condition is given. So this solution should satisfy this differential, this initial condition. Okay. So y of 0 has to be 2. If you plug in x is equal to 0, that should give you 2. This is actually, even though I wrote this as y, this is y of x. Okay. Y is a function of x. So let's use this initial condition to find the constant c. Y of 0 is equal to 2. That means the y value is 2 is equal to minus cosine. You plug in x is equal to 0. Cosine 0 plus c. Okay. That will give you c is equal to 3. Because cosine 0 is 1. You move this minus 1 to the other side. Okay. That gives you the solution. The solution is going to be minus cosine x plus 3. This is the solution that you're looking at. Okay. All right. Let's move on. Let's go to the next part. All right. The next example, again, I'm going to use separation of variable dy over dx is equal to y squared. That's the differential equation we have. I'm going to use this theorem. Okay. I'm going to bring my qy to the left-hand side as 1 over qy. That becomes 1 over y squared dy. Of course, I need to have the integration is equal to 1 times dx or just dx. Okay. So, and of course, I need to have the integration. Now, all we need to do is to integrate this. Okay. If you integrate your left-hand side, you get minus times y to the power minus 1 plus a constant. I'll put the constant on the other side. The integration of 1 dx is just x plus c. Okay. Now this is y to the power minus 1 is 1 over y. This becomes minus 1 over y is equal to x plus c. That means your y is equal to minus 1 over x plus c. Now, similarly, in a similar manner as in the previous example, I can use this initial condition to find this constant c. Okay. When I plug in x is equal to 0, my y value is 3. So let's plug in the initial condition there. Maybe push this a little bit upward like this. So we have initial condition y of 0 is equal to 3. That implies that 3 is equal to minus 1 divided by 0 plus c. Now you can solve this equation to find your c. That will give you your c value. Your c value is going to be, of course, minus 1/3. That means you have your solution. Your solution is going to be y is equal to minus 1 divided by x minus 1/3. That's your solution. Okay. All right. That completes the second part. And let's quickly do the third part. Let me copy the third part to the. All right. For this one also, to solve this one, again, I'm going to use separation of variable dy over dx is equal to, I'm going to pull out y. That will give you 1 plus y times 1 plus x. Now I can use the same technique. I bring the y terms to the left-hand side. 1 over y dy, of course, you need to have the integration, is equal to integration 1 plus x times dx. I'm just using this theorem, theorem 6.17. Okay. All right. Now let's do this integration. Integration of the left-hand side is ln absolute value of y. And then integration of the right-hand side is x plus x squared over 2 plus a constant, of course. Now you can find the constant using the initial condition given. Before we find the constant, actually we can solve this for y. Absolute value of y is equal to e to the power x plus x squared over 2 plus c. As you can see, e to the power something is always positive, so I don't really need this absolute value. I can write y is equal to just e to the power x plus x squared over 2 plus c. And notice that since this is a summation, I can separate out this constant. This is going to be e to the power c times e to the power x plus x squared over 2. Okay. Now this is again a constant. E to the power c is a constant. C was a constant. So e to the power c is another constant. So let me put a different constant now. Y is equal to a times, where a is a constant, e to the power x plus x squared over 2. That's my solution. Now I can use the initial condition to find the constant. Y of 0 is equal to 2. Yeah, given that y of 0 is equal to 2, that means 2 is equal to a times e to the power 0. That gives you, e to the power 0 is 1. That gives you the value of a, which is 2. Okay, so we have the solution. Our solution is 2 times e to the power x plus x squared over 2. Okay, that's going to be our solution. All right, that completes that example. Let's move on. Okay, next thing I want to talk about is the slope field of a differential equation. Let's go over this definition to understand the slope field of a differential equation. Definition 6.18. Given a differential equation, dy over dx is equal to g of x comma y, and the lattice of points in the plane, the associated slope field is a collection of line segments drawn at each point x comma y in the lattice with the property that the slope of the line segment drawn at x comma y is equal to g of x comma y. Okay, that's the definition of a slope field for a given differential equation. To understand what this tells you, what we mean by the slope field for a differential equation, let's straight away look at an example. Okay, here is the example that I want to go over. All right, let's look at this example. Sketch a slope field for the differential equation dy over dx is equal to 2xy on a lattice of points contained within -2, within x is between -2 and +2, and y is between -10 and +10. Then use the slope field to sketch graphs of 3 approximate solutions of the differential equation. Okay, clearly this is of the form, this is your function g of x comma y, right? This is of this form, dy over dx is equal to g of x comma y form. Okay, so we have that form. We need to sketch the slope field for this differential equation. So what do? First thing that we do is we take a lattice of points. Okay, so here is my lattice of point. I take 0.5 to be the step size along x-axis, and then I take 2.5 to be the step size along the y-axis. This is 5, this is 2.5, right? This is 2.5, this is 5, this is 7.5, this is 10, so on and so forth. Here, this is 0.5, this is 1, 1.5, 2, so on and so forth. And then at those points at that lattice, you need to calculate the slope. For example, if I go to this point, 0.5 comma 2.5, this is that point, right? This is the point. Let me actually mark that. This point is this point is 0.5 comma 2.5. What I do is now I go to my differential equation and plug in the x and y values at that point. X value is 0.5, y value is 2.5. I plug in x is equal to 0.5, y is equal to 2.5 there and find dy over dx. Remember, dy over dx is the slope of the tangent at that point to my solution curve, right? So my dy over dx will be at that point. Dy over dx at the point 0.5, 2.5 will be equal to 2 times 0.5 times 2.5. That is going to be 2.5. That means your dy over dx is 2.5 at that point. At this point, your dy over dx is 2.5. That means the slope is 2.5. What I do is I draw a small line segment with that slope, with a slope of 2.5. I do the same thing at each lattice point. The next lattice point is 0.5, 5. This is my next lattice point. Okay, I plug in this point, x is equal to 0.5 and y is equal to 5 in my g of xy and find the slope again. And I find that slope and then I draw a line segment with that slope. Small line segment with that slope at passing through that particular lattice point. Okay, so on and so forth. You draw a line segment at each point in your lattice. Okay, what does that line segment do? You take that point, plug in that point in your gxy, you find the slope dy over dx, and with that slope you draw that line segment. Okay, you draw these line segments everywhere. If you draw these line segments everywhere on your lattice, this is the picture that you are going to get. Okay, for example, if you go somewhere here, your solution curve should look like this at that point, because that is the slope of the tangent to your solution at that point, right? So that means your solution would approximately look like this. And if you are going to point somewhere here, your solution would look like this. If you are going to point somewhere here, your solution would look like this. This gives you a way to predict the shape of your solution curve. As you can see, you can have a nice solution curve like this, following this pattern, right? That is the idea of that is the advantage of having a slope field. We can see the shapes of your solution curves. Of course, you get a family of solution curves, right? You can see the shapes of those family of solution curves. And I have drawn 3 of such solutions curve. One curve will be like this. And notice that at the y-axis, on the y-axis, the slope is always 0. This tangent is 0. See, slope of this line segment is 0. That means on y-axis, your curve should be passing through like that. Right? You should have a horizontal tangent whenever your curve passes through the y-axis. And other points, you follow this pattern of this line segment to draw the shape of the shape of a solution curve. Okay. All right. Before that, I have only plot 3 curves here because we are asked to plot 3 curves, and you should be able to draw more curves. Okay. For example, you could have a curve like this, following the patterns of those line segments. Okay. Because near each line segment, you know that the curve behaves like that line segment. Here, your curve behaves that line segment. So you follow that pattern, draw the solution curves. All right, let's move on. Okay, the next thing I want to talk about is Euler's method of approximating the solution of an initial value problem. Okay, this is a method that you can use to solve an initial value problem. This is a numerical method, so you get an approximate solution. Okay, this is not a way to get the exact solution of a differential equation. It's an approximation. All right, first let's go through the statement of this definition, and then I will explain you the geometry behind this idea. Given an initial value problem with the differential equation dy over dx is equal to g of x comma y, an initial condition y of 0 is equal to y of x of 0 is equal to y of 0, and given a value delta x greater than 0, that is what we call the step size, define a sequence of points xk comma yk by the iterative formula given here. Okay, the iterative formula is xk plus 1 comma yk plus 1 is equal to xk plus delta k comma yk plus delta yk. Xk first coordinate is xk plus delta xk comma yk plus delta yk, where delta yk is defined this way. Delta yk is g of xk comma yk times delta x. Okay, you should be able to see that this is an iterative process, because to find xk plus 1 comma yk plus 1, you need the previous detail in the previous step. In the previous step, you have xk and yk. If you know xk and yk, you can go ahead and find xk plus 1 and yk plus 1. And then if you know xk plus 1 and yk plus 1, you can go ahead and find xk plus 2 and yk plus 2, so on and so forth. That's why we say that it's an iterative procedure, okay, process. So if you know the previous step, you know the next step. You can find the next step using the previous step. That kind of a process is called an iterative process or an iterative form. This sequence of points forms an Euler's method approximation to the solution y of x of the initial value problem. This method is called the Euler's method. Okay. All right. Let me briefly explain the geometry behind this. First of all, this is my differential equation. Dy over dx is equal to g of x comma y. And then the initial condition is given. Y of 0 is equal to y of 0. Let's say y of x of 0. Y of x of 0 is equal to y of 0. Okay. So here is the idea. Suppose somehow you know the actual exact solution of this differential equation. Let's say your exact solution looks like this. This is your exact solution. Okay. And then what you do is you start with this initial condition. Let me place this a little bit to the left. Your x-axis, y-axis. This is the point x naught, and this is your y of x naught. Y of x naught. That's the initial condition, right? Initially, your solution curve should be here. Okay. So at x naught, your y value should be y of x naught. Okay. This is the initial point. This is the actual solution. We need to find a way to approximate this actual solution. The idea is that what you do is we first calculate the slope of this solution curve at this starting point. To find the slope of this solution curve at this starting point, all you need to do is you plug in this starting point in your g of x comma y. You plug in x naught here and y naught here. That will give you the slope of the starting point, right? Slope of your solution curve at the starting point, because this is dy over dx. Dy over dx is the slope of your solution curve. If you plug in x naught and y naught here, that will give you the slope of the tangent at this point. Now what I'm going to do is I'm going to draw a straight line with that slope. I'm going to draw a straight line with that slope. And then, yeah, first of all, let me mark my x1, x2 on the x-axis. This is your x1. And then this is your x2, x3, so on and so forth. And this is the size of delta x, okay? This is delta x everywhere. Step size is same. Delta x, delta x, delta x. It's delta x everywhere. Okay. Now what I do is, as I said, I find the slope of the tangent at this point, and with that slope, I draw a straight line segment. And then I continue along that straight line until I reach the next point. Next point is x1. I reached x1 at this point, right? There I stop. When I reach the first point x1, I stop there for a rest. Okay. Now I direct myself. So remember, I want to find an approximation for this exact solution, right? So if I want to direct myself, if I direct this way, it is not going to work, right? I'm not going to find an approximation. I'm deviating away from the solution. I want to deviate this way, right? I mean, this way. And then after I go here, you deviate again. After I go here, I deviate again, so on and so forth. That's the idea, okay? Once I come to here, how do I deviate? To make sure that I am following this curve. I want to stay close to this curve. What I do is, I plug in this new point. This new point is now x1, y1. This is the new point x1, y1. Okay. Now what I'm going to do is, I'm going to plug in this point in my slope function, x1, y1. Then that will give a slope at that point. That slope is approximately equal to the slope at this point. Would you believe that? If you plug in x1, y1 here, that will give you a number. That number is approximately equal to the slope of the actual solution at this number. That's because these 2 points are very close. I take my delta x to be very small. That way, these 2 points are very close. If these 2 points are very close, if I plug in a very close point here, then the slope, when I plug in this number in g of x, y, that will be approximately equal to the slope of this, slope of the tangent at this point, right? The tangent at that point look like this. Now what I do is, I take that slope. With that slope, I draw a straight line segment like this. I continue until I reach my next point, x2. I stop here. Again, I do the same thing. I plug in this point. I plug in this, let me draw that line. I stop here when I reach my next point, x2. Now I plug in, this is my x2, y2. Now I plug in this point again in the function g of x, y. That will give you an approximation to the slope of your actual solution curve at this point, because these 2 points are very close to each other. Okay. Now what I do is, with that slope, I know the slope now. Okay. With that slope, I draw a line segment again like this. Okay. As you can see, every time I keep changing my direction and I try to stay close to my actual solution. That's the idea of this Euler's method. Okay. All right. Now let's go ahead and work on an example. This is so straightforward as a process, but you need to know the geometry. You need to know what's going on geometrically. That's what I explained here. But the process is very straightforward, okay? Even though calculation-wise it's lengthy. Let's go over this example now. Consider the differential equation dy over dx is equal to y with initial condition y of 0 is equal to 2. Use Euler's method with delta x is equal to 0.25 to approximate the solution y of x to this initial value problem on the interval 0, 2. Okay, going back to the previous explanation, we are given a differential equation. This time this g of x, y is known. You need to find this approximate solution. This is the approximate solution. Okay. All right. So we are given delta x. Delta x is 0.25. So how many subintervals are we talking about here? Well, we know that delta x is equal to 0.25. That is b minus a over 2. That is 2 minus 0 over, pardon me, n. So n has to be 8. So we are talking about 8 subintervals. Of course, you can solve this equation for your n, right? So if you solve that, you will get n is equal to 8. That means we are talking about 8 subintervals. You always start with x0. Your last one will be x8. Okay. This is x1, x2, so on and so forth. This is x7, x8. Okay. All right. Now we need to approximate your solution at each of these points. Okay. So the procedure is clear. This is the iterative process. Okay. Your xk plus 1 comma yk plus 1 is given by xk plus delta x comma yk plus delta yk, where yk delta yk is defined by this quantity. Okay. Here delta yk is defined by this quantity g of xk comma yk times delta x. Okay. All what you need to do is you start with initial condition. X naught y naught is given. That is 0 comma 2. When x is equal to 0, your y value is 2. So that means x naught comma y naught is 0 comma 2. You start with that point. You plug in k is equal to 0 in this formula. If you plug in k is equal to 0 in this formula, in the left hand side you get x1 comma y1. Right? Plug in k is equal to 0. So we can find x1 comma y1 to be x naught plus delta x. That is when you put k is equal to 0 here, you get x naught plus delta x, and then y naught plus delta y naught. But delta y naught is, by this definition, g of x naught comma y naught times delta x. But x naught y naught is known. This is the expression you get. X naught y naught both are known. You can plug in x naught and y naught in g of x to find this quantity, and of course the delta x is fixed, which is known, which is 0.25. If you plug in those numbers, you will get this quantity. Okay, and that will simplify to this coordinate pair, of course, that will simplify to 0.25 comma 0.25. This is your x1 comma y1. Value of x1 is 0.25, value of y1 is 2.5. Pardon me, this is 2.5. Okay, now I'm going to find x2 comma y2. You follow the same procedure. In this formula, this time you plug in k is equal to 1. Previously, you plugged in k is equal to 0. Now you plug in k is equal to 1 because you know x1 comma y1 now. Okay. If you plug in k is equal to 1, you get in the left hand side x2 comma y2. That's what you have here. And then here you get x1 plus delta x, y1 plus delta y1. Delta y1 is defined by g of x1 comma y1 times delta x. So this is what you get if you plug in k is equal to 2 in your iterative process. Okay. Now, of course, this is known. This is known. Delta x is known. You can plug that in. And of course, you can find this. G of x1 comma y1 can be found by plugging the value of x1 and y1 here. Of course, there is no x here, but you can plug in the value of y here, right? So if you plug in that value, you will get this particular value, pardon me, 2.5 as your g of x1 comma y1. And that will give you this coordinate pair 0.5 comma 3.125. And you do the same thing for the other points. You find all the other points up to x8 comma y8 using the same process, same iterative procedure. Okay. And that will give you a set of points. This is the first point, second point, third point, fourth point, so on and so forth. Now, if you plot those points, you will get the solution curve. If you plot those 8 points, yeah, and if you join those points with line segments, you will get the solution curve. Okay, that's the idea. And basically, this is the approximate solution. These coordinate pairs. Once you have the coordinate pairs, of course, you have a graph, right? You can join those coordinate pairs with the line segment, so you have a solution. All right, that completes that example. Let's move on. Next, I want to go over this theorem, Theorem 6.20, exponential growth and decay models. Okay, if a quantity Qt changes over time at a rate proportional to its value, then that quantity is modeled by a differential equation of the form dq over dt is equal to k times q. For some, here the details are given. For some proportionality constant k, where k is greater than 0 represents growth and k less than 0 represents decay. the solution of this differential equation that satisfies the initial value q of 0 is equal to q of naught is given by this expression. Q of t is equal to q of naught q naught times e to the power kt. Of course, you can solve this differential equation. This is a differential equation that you can solve using known techniques. What you do is you bring your q to the left-hand side as 1 over q. dq is equal to k times dt, right? Now you integrate. You know how to integrate this one. You know how to integrate this one. Of course, you can find the integration constant using this initial condition. Q of 0 is equal to q naught. And if you find that, you will get q of t is equal to q naught times e to the power kt. Okay. And of course, if this model is a growth model, k is positive. If it is a decay model, this k is negative. K is negative means this whole thing is negative. That means this rate is negative. Rate is negative means it's decreasing, right? That's why we say it's a decay model when k is negative. When k is positive, of course, the slope is positive. dq over dt is positive. So your population is increasing. Population or whatever the quantity that you are concerned of. All right, let's move on. Here is the next theorem that I want to state. Logistic growth model. If a population PT has natural growth rate K and is restricted by a carrying capacity L, then it can be modeled by the differential equation dP over dt is equal to K times P times 1 minus P over L. Okay, L is the carrying capacity. The solution of this differential equation that satisfies the initial value P of 0 is equal to P naught is given by this expression. Your population P of t is equal to L times P naught divided by P naught plus L minus P naught times e to the power minus kt. Okay. And of course, you can show that this is the solution of this differential equation using the techniques that you have learned. All right, let's move on. Here is the next theorem that I want to go over. Theorem 6.22, Newton's law of cooling and heating. Here is the statement of the theorem. If an object with temperature T of lowercase t, T is the time, okay? Uppercase T is the temperature. T of t is placed in a location with a constant ambient temperature A, then the temperature of the object can be modeled by a differential equation of the form d uppercase T over d lowercase t is equal to k times A minus uppercase T for some proportionality constant k. The solution of this equation that satisfies the initial value T of 0 is equal to T naught is given by this equation. Again, I'm not going to prove this one because this is so straightforward, okay? Because all what you need to do is you need to solve this differential equation. You can solve this differential equation using the theorem that we discussed today. So you can bring your 1 over A minus T to the left-hand side. dt should be equal to just k, d lowercase t. And now you integrate. You just use separation of variable. You bring this term to left-hand side as 1 over A minus T, and then you move this dt to the other side, and you know how to integrate this. And you integrate this and you isolate your T. That's all you do. And of course, to find the integration constant, you use the initial condition, okay? Then you get this formula. What I want to do next is to go over an example, which is an application of this theorem, theorem 6.22. Let's go over this example. Suppose your teacher sets down a fresh cup of coffee into a table in a classroom that is kept at a constant temperature of 68 Fahrenheit after giving a fascinating 45-minute lecture on differential equations. She remembers her cup of coffee, which has now cooled to a lukewarm 75 Fahrenheit. Assuming that the proportionality constant for Newton's law of cooling in this case is K is equal to 0.065. How hot was the coffee before the lecture started? Okay, this is a straightforward application of Newton's law of cooling. First of all, notice that the room temperature is given. The ambient temperature is given. In the formula, remember in the previous theorem, A is the ambient temperature. So, or the room temperature, you can plug that in here. So I plug in 68 here. I replace A by 68. And the proportionality constant is given. K is given, which is 0.065. I plug that in. Now all I need to do is I need to solve this equation. Okay, so I can solve this equation. This equation becomes 1 over 68 minus t dt is equal to 0.065. Let me write it over here. You get integration of 1 over 68 minus t dt. In the right hand side, you get integration 0.065 dt. Okay, so if you integrate this, you will get minus ln 68 minus t is equal to 0.065 t plus the integration constant. Okay, so that's the general solution. By the way, I'm skipping details here. Okay, you know how to integrate this kind of a function. You know how to compute this kind of an integration. If you integrate that, you will get this one. Okay, from this one, we get t is equal to 68 minus b times e to the power minus 0.065 t. Okay, you might be wondering how I got this particular t. For that, you need to isolate t from this equation. You need to solve for t. If you solve for t, you will get an equation like this. Okay, of course, this b is another constant involving c. Okay, you should be able to do that simplification. Okay. All right, this is the solution. Now I can use my conditions, some of the conditions given in the problem itself to find b. What condition can we use to find that constant b? Notice that after 45 minutes, the temperature is given. We are given that after 45 minutes, the temperature is 75 degrees. That means T of 45 has to be 75, right? That's the condition that we are given. We can use this condition to find this unknown constant b. Okay, let's go ahead and find that constant. All right, T of 45 is equal to 75. If you plug in lowercase t is equal to 45, your uppercase t should be 75. That means 75 is equal to 68 minus b times e to the power minus 0.605 times 45. Okay, from this one, you can find b times e to the power minus 0.065 times 45 should be equal to minus 7. Okay, so b is equal to minus 7 divided by e to the power minus 0.065 times 45. Okay, and if you calculate this, this will be approximately equal to minus 130.44. So that means we have the solution. Our t is equal to, if you want, you can write t of t, because we know that this is a function of lowercase t. So if you want, you can write t of t rather than just writing t. Okay, this is equal to, I can plug in the constant b now, 68 minus times minus, it becomes plus 130.44 e to the power 0.065 t. Okay, that's the solution that you get. Now, what does the question ask? Question asks you to find how hot was the coffee before lecture started. That means you need to find the temperature when T is equal to 0, right? That's what we need to do. We need to plug in T is equal to 0. That's when the lecture was started. So if you plug in T is equal to 0 there, you get 68 plus 130.44 times 1, right? That's because this whole thing is 1 if you plug in T is equal to 0. So the temperature was 198.44 approximately. Okay, this was the temperature before the class was started. All right, that's the last example that I wanted to do in this section. And with that, we conclude section 6.5. And we also conclude our Calculus 2 course. And we will be starting Calculus 3 course soon. All right, I'll stop there. I will see you in Calculus 3.